So that wraps it up for today. We've covered how our friend Clemency Hopkins, the mob boss, the cafe manager, that guy is the guy you need to see about nutrition. He's everything you need to know. We've learned how root zones mediate cannabis nutrient uptake, and how different physical and chemical properties of those root zones across different substrates, how that affects nutrition. We've learned through current research some of the nutritional requirements of cannabis. We've learned how different substrates affect cannabis. And today you have a roughly speaking holistic view on cannabis nutrition. You have the tools now to speak the language, to understand the bigger picture, and I hope this will help reduce some of the common mistakes that are made. And I really don't want anyone's plants to be limiting in any nutrient. So please like this video, comment below if you have any questions about anything. I'll do my best to get to them. Go over what I like to refer to as the root zone matrix, and any substrate that you're growing in, whether it be soils, a true soil, or a soilless mix such as peat, coconut coir, or rock wool, it's going to exist as a matrix of solid, liquid, or gas, and the proportion of each really helps dictate the success of your cultivation approach. And we'll discuss a little bit more about this as we learn more about the physical and chemical properties between different substrates. So let's go through the matrix. So not the matrix, but the substrate matrix. And that is really this zone of, so these are, let's say, solid particles, and we'll have in blue, we'll have our liquid water in here. So I've gone ahead here and very crudely with terrible colors and probably illegibility drawn the substrate growing matrix, and that's a continuum and a varying composition of the three phases: solids, liquids, and gases. So you have here the small bubbles are air spaces, those are your gas phase. You have larger solid particles in soils, these are normally clay. In soilless mixtures, this will be your peat, your humus, or your coir. And then in red is the root, and of course in blue is water or liquid. So again, that's just very crude, but to help try to get you to understand that soil or soilless media and substrates are a continuum of ever-changing phases of liquids, solids, and gases. And this is really important because this is what mediates cation or anion. So positively charged ions are cations, negatively charged ions are anions, and the ion exchangeability depends a lot on this interaction in the matrix. And what that really looks like is, if we have our root here, this is our root. What our root is doing is it's actually sending out hydrogen protons. So the root is doing this. It's exuding protons, and this is why pH is important. It's the percent of hydrogen or hydronium in the solution, and that really dictates what nutrients are available. So you have these protons coming out and then attaching. We just kind of draw our roots a little bit better here. It's the apical meristem, and you can have the soil surface here. We have our hydrogen Okay, so I've gone ahead and just drawn a root here. So this is your apical meristem. Cannabis is a dicot. And what ends up happening in the matrix is the roots themselves are exuding protons or hydrogen or hydronium. And what's happening is that in exchange for these protons, the roots are drawing in the ions available in dissolved solutions. So those would be positive things, cations like calcium, which is 2+. Calcium 2+, could be potassium. So here you have potassium. And then usually nitrate is an anion, so that's coming in this way, being absorbed, and that's a negatively charged particle. So what's more than this is that you can Okay, so I've just gone ahead here and drawn that we have our protons coming out of the roots, and then what's happening is that a bunch of ions available in cationic and anionic form, so both positive and negatively charged ions of essential nutrients, are coming in and coming in contact with the roots here. So our friends calcium, potassium, and then nitrogen available as nitrate. It's also available as NH4+, which is ammonia or ammonium. And what else is important here is that here's our little solid clay particle. Clay or humus, like peat, have a lot of negative charges on them. So what you end up happening is these negative charges are attracting cations. And then these are subsequently interacting with the water solution and the root hairs. So again, there's ions floating around in solution here. The composition of solids, whether they're clays that are charged, the surface area, and the amount of ions, so hydrogen protons and essential nutrients, that is a really complex interaction, and all of it together really represents what's available. And I just want to quickly point out that this is a common term, which is cation exchange capacity. And that you'll see often as CEC. So that's one definition there. Here, electrical conductivity is equal to the just total ions. So the cumulative charge of all of the ions dissolved in solution is its electrical conductivity. It does not tell you what concentration of each ion is in solution, and we'll discuss that later. It just tells you the total charge from all the ions. Then cation exchange capacity lets us know how much exchangeability there is between clay or humus particles, negatively charged particles, and solution, and subsequently the roots. And then pH, sorry, it should be lowercase, is our percent, so P, hydrogen or protons. And That's why pH dictates nutrient availability. More important physical properties of a soil that really dictates a bunch of other physical chemical properties and subsequently nutrient availability is its particle size, and more specifically its particle size distribution. So the relative amount of large particles to small particles, and you can get a sieve and weigh the amount or weight, the mass base concentration of each particle size with a set of sieves. But really briefly, we can draw a simple graph that helps demonstrate the relative importance of particle size. So if we start with clay over here, silt in the middle, and sand as going this way in particle size. So sand has a very high particle size. So this is an increase in particle size. So as particle size increases, so that's going from clay, so you would have maybe loam over here, and then clay, silt, and sand. There's an increase in particle size. There is actually a negative exponential relationship with several other factors on the y-axis that are very important to nutrient availability and plant growth, and they dynamic between plants and soils. And those are surface area, absorptive capacity, swelling. So these help dictate water availability, and then finally cation exchange capacity. Let me just write this better. Okay, so this increase in particle size shares a negative exponential relationship with several other important soil properties that really mediate nutrient availability and subsequently plant growth. And those are surface area, absorptive power and swelling, which are really an inference on water availability, as well as cation exchange capacity. So one really often overlooked component of the root zone and nutrition is the respiration that's occurring in the plant and in the root zone. So respiration is carried out in all living tissues. Above ground tissues in a plant are bathed in an atmosphere that is rich in oxygen. Everyone take a breath, and you're breathing in about 20% oxygen. However, when you saturate substrates or soils, and especially when they become compacted and there's a lot of osmotic pressure, you are depleting the root zone of oxygen, and respiration is vital. So you can have all of the nutrients available that you want, but in the root zone, but without adequate oxygen, you're going to really run into a major problem. And I see this in the cannabis space a lot. And the amount of oxygen in the root zone and respiration as a process in cannabis cultivation is severely overlooked and not understood. So we're going to go through that. We're all familiar with the equation for photosynthesis, and that's light plus CO2 plus H2O is going to make us our cellulose or sugar, and that's C6H12O6, and then plus we get our oxygen, and we're just going to want to throw the old 666 on here to help balance out our stoichiometry. So we're all familiar with that, but what actually respiration is just the opposite way of the reaction, and this happens in the dark. So these are dark cycle reactions and are pivotal. So if we go the other way and just say that energy within the chlorophyll, within the photosystem, is driving O2 consumption, sugar consumption, and that's going to give us CO2 and H2O. And again, we'll add our 666 on there, and now it's all balanced. So that's the respiration dark reaction, and this is needed for this to happen. It is at equilibrium. It's a two-way street, and we cannot overlook that for respiration you need a lot of oxygen in the root zone, or else this just does not happen. So please keep that in mind. Start with the old mnemonic for remembering plant nutrients, essential plant nutrients that is, as well as constitutive or organic compounds that are necessary for plant growth. So the old mnemonic is our friend Clement C. Hopkins' cousin mob cafe manager. And this mnemonic reminds us of what elements are necessary. So we manganese, carbon, hydrogen, and oxygen, and those are what's called constitutive compounds or elements. Then we have phosphorus, potassium, nitrogen, sulfur, copper, zinc, molybdenum, boron, calcium, iron, and magnesium. And our constitutive are carbon, hydrogen, and oxygen. So those are constitutive, right? And we can call them elements. And then we have primary nutrients, and these are needed in most abundance. And what you'll find is the relative ratio of nutrients needed or ions needed is more or less matching what that ratio of availability is in the universe. And for life, this makes a lot of sense, and you'll see this across living organisms. So our primary nutrients, as most of you will be aware, are NPK, and those are primary nutrients. And then our secondary nutrients are our calcium, magnesium, and sulfur. And these are needed in secondary importance of abundance. Whoops, nutrients. And then finally, these last suite of ions are needed in very trace or minor amounts, but are absolutely essential for growth. And these are the other ones that are up there. So chloride, manganese, what else do we have? Copper, zinc, molybdenum, boron. In our deficiency video coming up, I'll talk a lot about boron. It's rather pernicious as a limiting ion, so keep your eye on boron. And then we have iron, again another ion that really needs to be kept track of, and magnesium as well, especially how it interacts with calcium. So that's our constitutive suite of things, and those are readily available in the atmosphere as well as normally in the substrate for plants. And then you have primary, secondary, and micro nutrients. Let's put micro nutrients that are needed in trace amounts and are usually dissolved in water as minerals or metals. So you might ask yourself, well, why are all of these elements really important? And just very briefly, if we were to draw a plant cell, And let's use a few different colors here. We draw a plant cell. We have our chlorophyll, our photosystems here. So this is, let's just say, what would this be? This would be photosystem 2. We can say photosystem 2, chlorophyll. And we have incoming photons as light. Okay, so we have chloride, manganese, copper, zinc, molybdenum, boron, iron, and those are our micronutrients that are essential but only needed in trace concentrations or amounts. So now if we want to look at, well, why are these nutrients important? All we have to do is quickly look at a cell and look at some of the photochemistry that occurs within the plant cell. So I've drawn one here. It's a bit rough and the specifics aren't too important, except just pay attention to how much of each element is really needed at just one step here. So you have light coming into chlorophyll, your photosystem 2. Sorry, it's not in green. All I have is blue right now. You need a molecule of water to drive this light reaction, and generated from that are our friends ATP, adenosine triphosphate, so there's lots of phosphorus there. Inside our chlorophyll, it's predominantly nitrogen, and at the center of each chlorophyll molecule is a magnesium ion, and that's why magnesium is a secondary nutrient, essential. So coming out of that light reaction, as we know, as we take a deep breath, you guys take a deep breath, that's oxygen generated from photosynthesis. And we have adenosine triphosphate and NADPH, and that goes into another set of reactions which again need a lot of nitrogen and a lot of energy. And those are the respiration and dark reactions, and those again generate these phosphate-rich ions. Now, the phospholipid bilayers of the cell are all phosphorus. The ions responsible for water movement are largely potassium-based, and calcium is also behaves as a transport ion within the cytoplasm. And calcium is also a structural component of cell walls. It helps for leaf growth and just general meristematic tissue growth. Sulfate is needed. Sulfate is reduced inside the plant and becomes a vital component of proteins. Got to ask ourselves, so what are the general requirements for each element or ion that is necessary for cannabis, and how does this change through time? So just to begin, there's a fundamental graph that helps understand how growth is regulated by leaf nutrient content, and that just looks like this. So if this is leaf nutrient content or concentration, might be better, but anyway, and then we have growth, so any growth metric up here. What we have is a unimodal relationship that looks like this. So what happens is that you have exponential growth that is limited here when nutrients are deficient. You have a critical range for growth. You have a sufficient, so when we have the asymptote or luxury, and maybe that looks a little bit more like this. And then we have a toxicity or a surplus. So that wraps it up for today. We've covered how our friend Clemency Hopkins, the mob boss, the cafe manager, That guy is the guy you need to see about nutrition. He's everything you need to know. We've learned how root zones mediate cannabis nutrient uptake, and how different physical and chemical properties of those root zones across different substrates, how that affects nutrition. We've learned through current research some of the nutritional requirements of cannabis. We've learned how different substrates affect cannabis. And today you have a roughly speaking holistic view on cannabis nutrition. You have the tools now to speak the language, to understand the bigger picture, and I hope this will help reduce some of the common mistakes that are made. And I really don't want anyone's plants to be limiting in any nutrient. So please like this video, comment below if you have any questions about anything. I'll do my best to get to them.